Good morning. I'm Bruce Taylor, Data Center Dynamics. And what a great pleasure it is to be back in San Francisco. Last year we discovered that people in San Jose, people in Silicon Valley, if you're right around the corner, they don't show up. But if they go into the big city, it's a trip. So, trip on. So this is a day dedicated to looking at the digital infrastructure that's enabling and driving and securing the transformation of the global economy. It's nothing less than that. Digital first, internet facing, cloud native, and smart as hell. The keynote package this morning is, I really think, quite amazing. And we're going to get to see it from several different perspectives. At the end of the day today, Dean Nelson's Infrastructure Masons will reveal and take comment on their new data center performance indicator. So we bracket the day with big ideas on both ends, things that are going to transform our cloud world. So whether it's in the thought leadership sessions during the day today, or it's in the expo hall, or on the solution stage, my ask of you is to go to sessions where you don't know, and that you don't know that you don't know. It's easy to go to sessions where you likely are the smartest person in the room, and I don't think that advances the conversation very much. So this is a conference about what's right now and what's next. And to prove our bona fides, we have our version of speed dating. We call it speed networking. And this first effort at that in the expo hall is on cooling technology. And there's probably still, after all these years, no more foundational service in the data center than how we cool electronics. And it's about to go through its own transformation. And you will see liquid everywhere, very fast now. So to the work of the day. So a show of hands out there, is there anyone here who has not used Autodesk tools in your career? Anyone? One. Well, you're going to get to see something today that's, I think, will change what you think about Autodesk. So I had a chance to work on a research project, I think 4 years ago now, and it was a little insurrectionist group at Autodesk and the MIT Media Lab, and I was astounded at what they were thinking about. So it's been a dream of mine to find the right way to bring Autodesk to DCD's infrastructure audience, the people who are designing, building, and operating the digital factories of the future. And Autodesk is doing it. Lloyd Taylor is chief of Autodesk Cloud Infrastructure. I very rarely, as you know, read bios of people, but this is a big league dude. His team is responsible for designing, building, and operating the global cloud infrastructure that supports a massive transformation about what we think about as design. His previous professional work includes developing a worldwide infrastructure platform for mobile social media companies. He also was responsible for re-architecting LinkedIn's infrastructure to deal with that company's explosive growth. I think it was all me, just a guess. I think I hit 14,000 this week. He also developed, implemented, and operated the infinitely scalable physical infrastructure for Google's hyperscale expansion. He also built out a worldwide performance measurement infrastructure for Keynote systems. And in history, he developed one of the very first managed hosting architectures while at Digex. Prior to his work in the Webscale world, he spent 15 years at Johns Hopkins University working and teaching internet engineering, as well as developing several major projects for NASA and the US government. So again, this is all a very long-winded way of saying Lloyd Taylor is a really big-time dude. So Lloyd Taylor.
Thanks, Bruce.
Very welcome, thank you.
So I'm just a guy who likes screwing around with stuff. And the problem is the stuff I like to screw around with is bloody expensive, so I got to find companies with a lot of money, let me screw around and come up with cool things. That's basically my career. And the basic other rule is I never take a job I know how to do. So that's kind of ADD, and then there's the ability to deal with this stuff. I want to look at a couple things today. And I guess we're not going to have clickers. So next slide, please. So rather than talking about theory and all the cool stuff and coming up with systems to beat the world's best Go master or play chess, I thought it'd be much more interesting to talk about real-world applications of both machine learning and generative design today. Machine learning is pretty well understood. There's a lot of stuff going on in that, but I don't think the work that's happening in construction, I think the technology in construction is just starting to benefit from some of this machine learning technologies. So I'm going to talk about a new product of ours. It's actually in beta called BIM-IQ, which is essentially a way of applying machine learning to manage construction risk. And then we're going to talk about two short examples of generative design. One of them is going to be manufacturing. How do you essentially use a generative design methodology to come up with a highly optimized system, one that a human mind probably could not come up with? And then the other is sort of in architecture. And the example there is a new office building we're putting up in Portland, and using generative design to actually think about how that architecture should work. So deep learning, fundamentally, if you look at major construction, which all of you are involved in one or the other, one of the biggest challenges is managing the risk of that construction project. If you think about it, a deep learning system, which is one that essentially allows you to teach a system how to find things you're looking for, and then give it new sets to find those things for you, is one very interesting way to think about this. So first of all, data capture. You have field notes, you have scans, you have point clouds, you have smart helmets, scanners. Pretty much anything that can be uploaded to the cloud can be the basis for machine learning. But if you're dealing with a field situation with a superintendent, that superintendent or his or her team are going to have to deal with thousands of issues every day. How do you know what's important? And just to make that more interesting, we discovered when we run the analysis, how do you know what high risk is? Well, it turns out that people are pretty good at identifying high risk things. So the highest correlation between high risk construction issues is those that the personnel consider high risk. The challenge is how do you get each of those personnel to roll that high risk thing up to the superintendent? Secondly, it turns out the most predictive thing for high risk in construction is water risk. So someone didn't finish the flashing, they didn't seal something, the rain hits, and then you have hundreds of thousands of dollars of loss the next day. So on top of that, you have thousands of issues, and you have hundreds of subcontractors. In general, when you're managing risk, what you're really doing is having to manage the subcontractor risk. The subcontractors are doing part of the work, they're doing some of their own inspections, but again, the superintendent's responsibility is to figure out who to talk to in what order every day to make sure the project is going on correctly. So what we did is, next slide please. The team that did this, and I'm the cloud guy, I don't get involved in product, which is probably to the best for the product. But the idea was a machine learning-based prioritization list seemed to be a good way to start this project. So we collaborated with a number of major construction firms, all who willingly allowed us to use their data to train the machine learning system, and essentially took all this input and then figured out which is the highest risk issue by contractor each morning for the superintendent to deal with. And what this does is allow us to do what's called an assistive predictive model, which is using all the data that's been generated and collected on the site, running an overnight machine learning process on it, and then doing a predictive list of what the risks are, essentially allows the superintendent not only to be using the field software, which keeps track of the normal field process and access to all the documents, but also a computer-generated risk profile. Now, the input to this, construction data sources. Any of you who have worked with machine learning, there's two steps. One is you have to have a training set, which is essentially a set of data which says when this happens, that happens, and you feed that to the machine learning system. And once it's trained, you can then feed it live data, and it will make predictions based on that live data, based on what it's learned from the previous systems. Then you have to build a model. So our model was to come up with a subcontractor risk score. So essentially, the output of the first machine learning system is here's a bunch of risks, but then the deep learning mechanism is to take that and convert that to a subcontractor risk score. And that then, one output of that is, superintendent, here is the 3 high-risk issues. You have these 3 contractors have high-risk issues, talk to them first. These 7 contractors have medium-risk issues, talk to them second. On the field, this is a real example. It's a fake customer. This is a real example of what the superintendent and their team will see. On the right is the normal field information. On the left is the predictive risk. But what's really cool is back at headquarters. Next slide, please. Here's the executive view. Every construction project that particular construction firm is doing on any given day, every morning the risk of that project is updated back at headquarters. So the risk management team, the finance team, the legal team, the management team knows where to put their attention that day to keep stuff on track. You start to see the power of this technology. Next slide, please. So the proof's in the pudding. One of our partners in developing this technology was Skanska. And they use this technology in beta form. They helped us build it along with Swinnerton and some other major construction firms. And their estimate is that this technology in beta form saved $6 million on this project they recently completed in New England. So that's pretty good. I mean, this is still a science fair experiment kind of stuff. And I think the tuning can get a whole lot better. Next slide. So machine learning is just a methodology. Anytime you have large data sets that you can use for training, you can take similar data and use that for testing. You have to learn how to do network training protocols. There are people who can do this for you, and a number of the companies are actually offering now expert systems. Here's the thing that's good for everybody in this room. These things take tons and tons of computing power. What's more, as the computing power becomes cheaper, they will use more of it, because the deeper your learning model gets, the more compute it requires, and the better it is at predicting things. So trust me, you all are in a great growth industry right now. But anytime some simple applications, and I hope the panel will touch on some of these things, are in operations optimization, in exception detection. When do you need to look at something? When is it important? One thing we all suffer from every day is massive information overload, and a system that can help us understand what's important to look at can save us a bunch of pain. So quickly, generative design, I'll give 2 examples. One is, first let's define it. Generative design is a methodology that allows you to mimic nature's way of building things, which is highly adaptive. Essentially, instead of putting in a plan, you put in a set of constraints, design goals, materials, construction methodologies, whatever, and then the cloud software simply can explore all possible solutions for that problem. The only limit to the number of solutions you can come up with is how much you're willing to pay for the compute time. Give you a very simple, give a straightforward example. Nothing simple in this space anymore. Next slide, please. So example one, manufacturing, Airbus A320. Airframe design and construction is very, very interesting because over 95% of the cost of an airplane is the run cost. It's keeping the thing in the air for the next 30 years. So generative design is essentially, we backed up here, let's see. So what we partnered with Airbus to think about just a partition. The partition is the part of the plane that the flight attendants' seats are connected to. It has to be very strong. It has to handle massive shock and still protect the attendants. But strong generally means heavy. So working with Airbus, we essentially came up with a design, or the system came up with a design, to absolutely optimize the strength of this device with minimizing the weight. So essentially, we go through an iterative process where we test all possible combinations of mechanical for this thing. We do stress testing, we do modeling, and ultimately the system comes up with a system that minimizes the balance between weight and strength. Then we use 3D printing technologies to create this thing, and then it's bolted together in the plane. Here's a simple output. These are a whole bunch of different design solutions. Essentially, the designer's role becomes one of moderator as opposed to designer. The person decides what is the best solution. And that's what the final thing looks like. That doesn't look like anything a human would develop, but it's stronger. It's twice as strong and half the weight of the human design method bulkhead. Quickly, in architecture space, we're building out a new office space in Portland for the Autodesk team there. And our office of the CTO said, well, people have preferences. People work together. We can characterize people actually as JSON objects, and then we can run a generative design on what is the best way to design the office building and the seating so that they'll be most productive and most happy. Next slide, please. So here's a layout of the building, Revit model. And we did a little human factors research and discovered there were sort of 6 things that define how happy people are in office space. So we then went around and categorized for each person who was going to be in that office space what their preferences were in this area. I suggested they should include a variable for whether they like puns or not, but that was rejected, so I'm sorry that isn't in the model. But you look at things like who do they work for, who do they talk to most. Conceptually, one could import calendars for the last year and see who they met with the most. That's a data source one could use with permission. What kind of lab space do they need? What kind of services do they need? Do they prefer it dark or do they want it bright? And then using generative design, you take that input. Next slide, please. And run the same sort of analysis we did for designing the bulkhead in the plane. You come up with thousands or millions of possible office layouts. Once you have them, then you can run simulations and analytics on them to understand how people will interact. And then once you've picked a few and really want to put some serious money into them, you can start doing things like insulation analysis. You can do things like how much people walk around, groupings, because one of the most distracting things in the office is people walking past your desk. Well, what if everybody you work with routinely is near you? The amount of wandering around goes down dramatically. So that allows you to essentially come up with a final set of ideas. And what you can then do is go to a 3D modeling package, taking the Revit model that's been generated from all this process, and you can sit everybody in the office down with a pair of Oculus goggles, and you can have them live in the space without ever building it. Because guess what? Models are never as good as reality. And it's very interesting watching people as they start experiencing the office space that hasn't even started construction yet. And the feedback you get then can go back in, because ultimately the purpose of a generative design or a machine learning model is to do something better for people. And then you get that feedback, and that goes back in the generative design model, and the next time you design the office, you can do it that much better. So that's a very, very brief introduction to a bunch of technologies that I think are changing the world. Next slide, please. The brains behind a lot of this is Jeff Kowalski, our CTO. This is a quote. I never read quotes on slides. I'm going to read this one. These technologies are not a threat. They're more like superpowers. It allows you to do better design, better operations, and better in general. But here's the real threat. Any competitor that adopts these technologies faster than you do is going to be turning out better product cheaper. So there's the risk. That's why we need to pay attention to these technologies. My job at Autodesk is to build out the cloud infrastructure to enable this technology to be available to anybody who wants to use it. Essentially, my job is to take 35 years of intellectual property in all the software that we built or acquired during that period of time and turn it into cloud services and build the platform on which anybody can build applications. So all of this stuff has become much more available over the next several years, and I think it's a very exciting time to be in this space. Thank you for your kind attention.